Hey everybody. So this week, I'm calling this Unit 4, Part 3, right? And this week, we're going to meet some data sets, and we are going to learn to use the Python libraries Pillow and PySoundFile to create our own data sets. So first, we're going to talk about two common data sets, MNIST and SciFar. So these are useful so that we have some common experimental data that's easy to get a hold of. These are useful because it's important to have some sort of common shared data sets that we can use as benchmarks. And you'll see MNIST and SciFar a lot. So there are a whole bunch of different ways that you can get these data sets. We're going to use the TF datasets optional module. It is not part of a baseline TensorFlow install, but you can get it with either pip or conda here. And it includes loaders for a whole bunch of common data sets, including the two we'll be talking about. All right. Oh, right, and you would import it this way, right? So wherever you see TFDS, that's a reference to TensorFlow datasets. Notice the hyphen in the package name, but the underscore in the import name, right? Do not be tripped up by this difference, right? So it is TensorFlow underscore datasets when you're importing it, but the package is TensorFlow hyphen datasets. All right. So first, let us talk about MNIST. MNIST, and I'm blanking what the M stands for. It's shortened from a handwritten digit data set at the National Institute of Standards and Technology. I think it is. I can't remember if it's Standards or Science and Technology. But it is a data set of grayscale handwritten digits between 0 and 9, each containing a category label. Okay? You can get it here. This guy, if you don't already know, is a major name in this field. Jan LeCun, I'm not sure how to pronounce it. But if you download the binary image from there, you will need to write your own parser. And while that's not very difficult, it's not a hard binary format, it is more work than we need to do. Many machine learning and statistical inference libraries include helper loaders for MNIST because it is an incredibly common data set, and we're going to be using one of those. So each pixel is an unsigned byte, where 0 is white and 255 is black, right? I think the phrase it actually uses is background and foreground, but you'll usually see it rendered as white and black. Note that this is kind of backwards from how you'd usually think of it, right? So the pixels inside of the images are going to be 0, and outside of them are going to be 255. So the easiest way for us to get this thing is TensorFlow datasets, right? And yeah, there are also a whole bunch of other loaders. Like scikit-learn also includes a loader that will yield you MNIST. And that looks, at its simplest, something like this, right? So here are my typical imports. Notice the addition of TensorFlow datasets as TFDS. I disable the progress bar. Normally it tries to pretty print a little progress bar, but in my experience, sometimes that blows up when you're running it inside of Spider, so we're just going to turn that off. And then we just call tfds.load with the name MNIST. So many of these data sets contain different splits. I think MNIST only contains these two, but I'm not sure. We are going to specifically tell it which of the two splits we want. We want the test set and the training set, right? And it's going to yield those two in a tuple that we can then unpack into a test and train data set. So what this is actually going to do is return us a tensorflow.dataset, right? So if you're wondering what this is going to get us, if you were maybe hoping it was going to give us a nice numpy.array, no such luck. It's going to give us a TensorFlow dataset. TensorFlow datasets can contain multiple features. It's actually a little inconvenient for us here So what we actually want it to do is to go ahead and package us the data in such a way that there is one input feature and one label feature, and that is what as supervised is going to cause it to do. That's going to cause it to return the data set in such a way that without much more processing, we can just drop it into a keras.model.train or .fit function and have it use this data. Okay? So we have to do a little bit of pre-processing. So again, remember that what we get, what train starts out as, is the result of that tfds.load, okay, and that it is of type tf.dataset. So TensorFlow has a very deep, rich sort of model for these things, right? Datasets have a whole lot of complexity that we really kind of don't want to get into right now, all right? So for now, we're going to treat it a little bit as a magic box that we can call a couple of operations on and be done with, all right? So it contains, each item in the data set is an image and a label. If you look at the type, the image is a tensorflow.tensor. So the image is a tensor. And I forget exactly what the shape is. I think it's 28 by 28. But it is of type uint8, right? It's unsigned bytes. And our neural networks usually work in terms of floats. So what we need to do is convert every int image into a floating point image, and then normalize it from the range 0 to 255 to the range 0 to 1, right? The label component, on the other hand, is an integer. It is the index, right, of the correct category label. And since these are numbers, right, it's also just the index of the number, right? We've assigned category 0 the first category label, right, the 0th category label, and category 1 is the 1th category label, and so on, right? So it is also conveniently the digit that it is. But we need to convert these sort of just a number, right? It's just a number of the appropriate category label, and we need to convert it to a one-hot vector, right? Because that's what we actually expect at the output of the network. So how do we do that? Well, we can write a function that does that for one sort of sample from this data set, and then we can call map. So what this is going to do, so these TF data sets are designed to be composable and to represent you performing a bunch of composable operations on your data very simply, right? So what we do is we can call map with a function as an argument, and we'll get a new object that represents the result of applying this function to every object in this data set, okay? So map applies the function you give it and returns a handle to a new sort of data set representing that result. I believe it is the case that it does not do that immediately, right? It's going to be lazy. So these things are kind of designed, these TensorFlow data sets are designed for a kind of data center environment, right? Where you want to be able to build an efficient series of computations that can represent some non-trivial transformations and then sort of deploy those and have those happen only like as required, right? And so I believe that what this new object represents is the result of that computation, but that computation hasn't actually been performed. That computation will be performed on demand as we iterate through this thing, right? So the next thing we have to do, unfortunately, so if you look at the dimensions, I think it's actually 28 by 28 by 1. these things are designed to be composed in many batches. And there's not an easy way to cross off that little extra dimension. That extra dimension is basically the batch dimension. There's no easy way to get rid of it. So basically we're just going to have to also do a batch operation to break this large data set into little batches of 50. And again, this is not going to happen immediately. I believe this is going to happen as we iterate this, right, on demand. And we need to match up sort of whatever transformations we do on the test set, right? Because the input, the input format needs to be the same, right? If we're going to convert the training set images to floating point 0 to 1 images, we need to convert the test set to floating point 0 to 1 images. And, yep. Now let's look at some sample code.